Hello everyone, we are Wei Zhang and Hao Yuan. Today we're gonna talk about the hydrostatic lubrication, how to compute the hydrostatic pressure beneath a circular disc. At the very beginning, there's something we want to clarify. The hydrostatic lubrication is characterized by the complete separation of the conjective surfaces of a kinetic pair by means of film of fluid. Its distinguished features that are such as lack of wear, low friction, high load capacity, and so on. It also differs from hydrodynamic lubrication in that the contact pressure is generated by an external pump instead of by viscous drag. And the picture here it shows that how the system looks like. It is always used in equipment with extremely low speed as the hydrodynamic film cannot form. In this slide, the formation of fluid film in hydrostatic lubrication is presented. There are many four stages we shall look upon. At first, we can see that the pump is off and there is no recess pressure. Meanwhile, the bearing pipe contact with the bearing runner directly, and it holds all the load W. If we turn on the pump, the pressure in the recess pocket will increase and try to lift the disc, as you can see in the picture B. For picture C, once we continue to turn on the valve to increase recess pressure, the pressure times recess area will be equal to the normal applied load. Next, the pressure keep going up, and finally there won't be any contact between the pad and the bearing directly, which indicates the formation of the fluid film. Next thing, we will introduce the compensation. Compensation is a process by which the inlet flow is restricted in order to support varying loads. Hydrostatic bearings need a flow restrictor in order to support varying loads. The design of the flow restrictors is very crucial, as it determines the overall performance of bearing and the cost to some extent. For example, the constant supply pressure restrictors, which is generally used for compensation, and also the most commonly used restrictor are capillary and also orifice. These are the real application, the real thing of the supply pressure restrictors. When you have the dropping pressure from supply pressure to recess pressure, it is controlled by the fixed restrictor placed between the supply manifold and the bearing. And also, from the picture on the right corner, when you increase in the load, it reduces the flow by decreasing the film thickness on the bottom, and the recess pressure increase and the equilibrium is restored for the whole system. So the next thing we can talk about the theoretic analysis for the pressure file and also the loading capacity.
Here I'm going to show you how to calculate the pressure distribution and load carrying capacity for a hydrostatic bearing, which is also called a externally pressurized bearing. The reason why we call it externally pressurized bearing is because in the region shown here, which is called the recess, the pressure is provided by a pump, and the pressure in this region is kept as a constant, which is PR. For the pressure outside this contact region, the pressure is called PA. But we need to pay special attention to the annulus region, which is in between, because we all need to know what is the pressure distribution and how the pressure develops from PA to PR. To do this analysis, we should first look at the governing equation, Reynolds equation. Here I'm showing you the Reynolds equation defined in polar coordinates. For the first two terms on the left-hand side, these are the pressure terms. And for the first two terms on the right-hand side, they are the wedge terms. And the last term is a squeeze term. But actually, we can simplify this equation because for hydrostatic bearing, in train velocity Vr and V theta are considered to be 0, so we can cancel out these two terms directly. And also, we are considering a steady state condition, so we can also cancel out these terms. So we only have the pressure terms, and the right-hand side is 0 now. But also, we all need to make some assumptions. First, we all need to consider the pressure is independent of theta, which means pressure only changes with R. So this term is also 0. And second one, in the recess region, where R is smaller than Ri, the pressure is equal to PR. And thirdly, we consider the fluid is incompressible, so the rho is a constant. So for now, the Reynolds equation can be reduced to this form. And also, since in our analysis, rho, h, and eta are constants, so we can take them out. And also, for pressure, it's only a function of R. So we can rewrite this equation like this: ddr r dpdr equal to 0. Then we can calculate the pressure distribution by integrating this equation. And starting from this point, you can first integrate it once, like here, r dp dr equal to constant C1. And then we can bring the r term to the right-hand side, which gives us dp over dr equal to C1 over r. And then we can integrate again, so we have p equal to C1 log r plus C2, which is also a constant. So now we'll need to compute the values of C1 and C2 based on the knowledge of the boundary conditions. So in here, we have the first boundary condition, which is R equal to Ri, then P equal to PR. But here, it is second boundary condition, which gives us R equal to Ro, then P equal to PA. By plugging these two boundary conditions into this equation, we can calculate the values of C1 and C2. For C1, the value is PR minus PA divided by log Ri divided by Ro. And for C2, the value is PR minus C1, which is PR minus PA log Ri over Ro times log Ri. So now we have the expression for the pressure distribution in this region, which is a function of R. But since we already have the values for pressure in this region and in this region, that means we have the pressure distribution for the whole domain. And we can draw the pressure distribution like this. For the vertical axis, that is the pressure. And for the horizontal axis, that is R. And for R equal to 0 to Ri, P equal to a constant PR. And when R approaches RO, the pressure decreases and then finally reaches the value PA. Due to symmetry, you can develop this figure like this. So that is the pressure distribution for a hydrostatic bearing. And then with this pressure distribution, we can calculate the load carrying capacity. Considering the circular disc above the hydrostatic bearing have some load, we all need to know what is the maximum value for this, which is the load carrying capacity. Considering that the load carrying capacity can be calculated by integrating the pressure value over the area in contact, we can calculate the load carrying capacity by plugging the pressure values in different regions and integrate them to get a load carrying capacity. Considering that in the recessed region, which is shown here, the pressure is a constant PR, and in this region, the pressure is newly derived in the last slides. We can split the LCC into two forms. First, we'll need to integrate from 0 to PI to RI with pressure equal to PR. Then we can integrate from RI to RO with the expression we derived in the last slides. This one is the first term, this one is the second term. And since we are dealing with the circular disc, the area of contact is pi r squared, so that we have dA equal to 2 pi r dr. So the rest of the thing we'll need to do is to do some calculation for the first term. It's simply 0 to R1, Ri, then PR times 2 pi r dr. And the second term, we can do it in the same way, from Ri to Ro. Then use the formula we derived before to calculate the second term. Then the rest of the thing is to do something for math, which is not shown here. Here comes to the end of the video, and thanks for watching.